right, everyone, welcome. And here we go with Introduction to TensorFlow and Keras, brought to you by Eduonix. All right, so first thing I wanted to go ahead and start with, let me go ahead and, so I actually seen this article the other day, and it was like ridiculously relevant to what we're about to be doing. So depending on how many of your towards data science paid articles you've read, you may or may not be able to see this one currently, but if you want to save that link and read it later, I'm just going to talk about a few things in here. So this is looking at the 10 most in-demand data science skills in 2021. So if you look here, some of the more traditional type things are kind of falling behind here. So we're not really even seeing like an Excel or a Google Sheets, kind of those, backbone standards we thought of. Whereas now we see Python is kind of just really included. We're looking at percentage of job postings. Pretty much all of them are including Python. We're still seeing SQL and R pretty high up there. A typical rule of thumb with data science is you learn Python or R, and then you kind of get into SQL as well. However, if we look down here, another one that's pretty popular, or at least seems like it, is Tableau. However, again, if you compare how many jobs are requiring Python or desiring Python over Tableau, it's pretty impressive. We also see TensorFlow is hitting this, even if we just kind of specify just by skills in general. If you go down a little bit further, you can see that a lot of these are common packages we've already seen. And then here it's kind of breaking it down even a bit further, so you can see everything all the way going down for 25. And then this is programming language only, so it took out things like Tableau, which is just direct programming language. So again, kind of comparing just those, we still see Python with the lead. And then within the Python library, this is the one I found kind of cool just because it's all the things we've talked about and used so far. So Matplotlib, that was kind of our backbone for visualization. This ties in pretty well with Seaborn. Oh, no worries. Okay, awesome. If we're looking at this one, so again, we can kind of see this. These are fairly common. SciPy has some cool statistical stuff. You see NumPy, Pandas. As I've said, we kind of bring those in every time. We haven't talked so much about PyTorch yet. That's kind of a data management type thing. Scikit-learn, we've done a ton with. That's all of our machine learning. And then now we're going to be getting into TensorFlow the next 2 weeks. So you're kind of walking away with one of these big ones here where you have a lot of experience in these top 10. And then again here, it kind of throws some other ones here. So the overall pattern, so something worth looking at. We're seeing those shrinking skills here. So Hadoop is going downward, whereas that used to be very popular. Same thing with Hive, SAS, if you've ever looked into that, it's more of a paid software. So kind of cool how we can kind of see some of these cool takeaways here. So I just thought that was an interesting read. If you want to read more in depth later on, I would say more than welcome to, but we'll do a little more than just reading here. Okay, so another thing that I found out this week, and I've heard of it but never used it, but I took a little bit of time this week to kind of play around with this just because we did so much with predictions. And I found this really cool library / module package thing here. So Lazy Predict, we spent a lot of time building blocks of code. So if you kind of seen the last 2 weekends together, we put in these nice little blocks that help us optimize models and do some parameter tuning. This was a really cool import that I have officially started using in all of my code whenever I'm training models, whether it's for classification or regression. So we're looking at like 5. This one is going to kind of compare pretty much every single model you can think of, and it's broken nicely into classification and regression. I thought I had like the kind of landing page type thing a little bit more handy. So what this does basically is it pulls together all the different libraries, and then it kind of makes it look a bit nicer. So we're actually going to work through this example of it together today. So the easiest way to understand this one is just to go ahead and use it. So let's go ahead, and if you want to go and open up a notebook. So the first thing we're going to do here is we're actually going to have to use Anaconda, the command prompt, to install some things here. So while Jupyter comes with a ton of stuff, some of these less common or newer packages aren't necessarily pre-installed, as well as like TensorFlow. We're going to use the same kind of strategy when we do that today. So to get your command prompt open, you can do pip installs in here. I just prefer not to, because I'd rather just do it the full correct way. So if you go to your search menu here and you just type in Anaconda, It's this one here. So when I have this open, it's a bit hard, as you know, who's worked in a terminal environment. It's kind of hard for me to zoom in. So what I'm going to do is just type, and I'll share in the chat. So what I'm running in this is pip install lazy predict. And when you run it, you just press enter. And mine's already installed, so it's probably going to go a little faster. So I'll wait a few minutes here to make sure everyone gets caught up so they can use this. And when you install it this way, all your Jupyter notebooks have it that way. And then last thing you'll want to do is just restart your kernel here so that way it loads in. So kernel restart, just to make sure that it's got that installed. Otherwise, your import statement won't work. Here we go. So this is going to be that. Let me go ahead and get a snip of this real quick here. So here would be if you're on different OSs. So if you're running Ubuntu, you want to be here. So you're just going to install directly from the terminal if you're there. So same thing if you're here, if you're on a Mac, then instead of using the Anaconda command prompt, you're just going to use your terminal directly. And then if you're looking for those directions to open up on your end. Okay, so once we've got it installed, what we're going to do is go ahead just and import it. So we're going to say import lazy predict. Yep, the installation command is going to be pip install lazy predict. So all the imports you can see on my screen here. And then our warning here is just about this import. It's something different. They want to install utils, but it'll work fine for now. So we'll stick with that this time. So these are going to be our two that we're going to use here. So lazy classifier and lazy regressor. Wonderful naming convention by whoever created this package. So it's really cool. Again, once we get going here, I just kind of stumbled across this and gave it a try and matched up with the, the exact same output when running models the same way I've shown you thus far. So this is kind of that all-in-one skill set where it's going to run all of the models at once. It won't do any hyperparameter tuning. So like kind of how we played with some different inputs, we used a grid search to get the optimal model. That's not necessarily built into this. However, it will run all the models as defaulted. So that's kind of a cool feature here. So you can kind of see without any tuning how well different models do. All right, so we're just going to pull some data here from sklearn. So scikit-learn. This is going to be some nicely pre-built data sets. So if I'm going to go ahead and get one, we can say data is equal to load breast cancer. Okay, got an error on XGBoost error and cat boost. Okay, Larry, let's hang tight for now. I'll look up those errors in a bit here once we have a moment. I'll see if I can find a workaround for you. So for right now, we're just a cool another way, kind of how we worked with the seaborne data before. Here's another place to get data sets is just from using this vernacular here. So if you're looking at some other data sets, you can refer to as toy data sets, meaning they're kind of pre-established data. You'll notice the iris data set is in here, as well as a couple others. So we're using this one first. So just some cool different stuff here we can use. So kind of that pre-built data. So for working on different models and getting used to them. So the first thing we do is we're gonna go ahead and load that. Then what we're gonna do is get some data in our targets here. So I'm gonna say X is equal to data.data. And then Y is equal to data.target. So since it's pre-built, it's got some pretty nice import commands here, so we can kind of reference it pretty quickly. So this is just another way of getting it in here. And again, this would work on any data sets that we've used so far. The code might look a little different, just so you can isolate different columns. But again here, so we're saying this is our input data is the data, and then the Y is the target. Next thing we're gonna do is do our train test split here. So I'm gonna say X train, X test, Y train, and Y test. So we have train test split, and then X comma Y. So just referencing where our data is coming from. For test size, let's go ahead and just go with 0.3. And then for our random state, I'm just gonna stick to 1. So I'm gonna go ahead and put that over in the shared file now and give everyone a minute or two to get caught up with downloading that. And Larry, let me go ahead and take a look and see if I could find what this error was. Okay, Larry, another option might be here, something I found. So again, you can kind of try each of these. So you could run your pip install and just directly install those missing packages. So XGBoost, and then cat boost, if those are the two that are missing. And then the other one that it's saying might be a issue would be pip install light GBM. So if you're getting that issue, you can try those as well if that one you found didn't work. All right, so we've got this. I'm gonna go ahead and run what I have on here. So if I take a look at the data, it's gonna be an array. So this is a classification array. So it's giving different measurements here and the true or false output here. So the 1s and 0s are true, false, either success, failure, has, does not have. Then here's the different measurements inside. So that's kind of what our data is looking like there. So the Y is just those 1s and 0s, and then the X is the input data there. Here, our training and our testing data. So we did a 70-30 split. So 70% of the data is being used for test, whereas 30% we're saving for, or I should say 70% is used for training, 30% is being saved for testing. And then here, let me go ahead and get you guys this in the code. Our next lines. So we have CLF, so that's just gonna say a classifier. So a lot of times when people build classification models, CLF is a nice shorthand to use for that. So we're gonna use lazy classifier. Verbose, we're actually gonna play with this a little bit too, just to kind of see what the differences are there. Let's start with it being equal to 0. And I'll type this out and then walk you through what it actually means. What is it saying? Oh, I forgot to put in my X test data. So X train, X test, Y train, Y test. There we go. All right, so this output here, so it's built in even with a nice little bar in here, which again, depending on the machine you're running on, may take longer or shorter than mine. It also depends on how complex your data is. The reason why we're doing the demo with this set of data is because it's pretty straightforward. It's just an array of numbers, so it'll run pretty quickly. A couple of options here before we actually look at what these models look like is this argument of verbose. It's one of those things that a lot of different packages have. So what it does is it shows you different levels of information while something's executing. So while it's fitting here. So if I set it to 0 and all it showed me was this bar, if I set it to 1, you can see a little bit more going on in here, right? So it's showing me each iteration here of each of the different models. So you can see those real-time updates of how they're performing. So again, the reason we typically use 0 is just because it's much less annoying to see. So I do recommend that you again stick to verbose being 0. However, the higher of a value, the more you see of what's occurring. So I always kind of say like, hey, maybe one time set it to 1 to see what the code is doing. However, if you want to make it more readable for yourself later on, Sticking to 0 is kind of optimal there. Okay, all right, let's go ahead now and let's see our different options. So if I just call models, it looks pretty cool. If you know, for some reason, a lot of people say they do it like this, and I don't like how that looks. I find that kind of ugly. So I just like to call on it directly of models. And we get a nice little table output here. So if I'm taking a look at this, it gives me my different measures here. The only thing that looks nicer is when you hit print is all of this isn't a line, but this is actually a group by object that comes out of this, I believe, just with the formatting here. However, we can see a lot of cool stuff here. So we have our accuracy, balanced accuracy, and again, this is classification, hence why we're looking at accuracy. ROC, AUC, so that's going to the return area under the curve. We have our F1 score, and then how long it took, so time taken. So this is something that we don't do a whole lot with when we're doing these kind of intro level tutorials. However, as you build out things on larger data sets, time taken is actually fairly of a concern depending on how often you need to run a report. So for example here, if I look at these ones that are higher time taken, now this is like, I believe it's measured out in seconds or possibly milliseconds. But like here, this 0.21, where was it? It was a high one. So my random forest classifier, now it was a pretty accurate model, but it also took notably longer than the others. So it's one of those things where it's like, depending on the size of your data, the time taken may be an issue. So it all gets down to the type of data work you're doing. For example, I report for the American Board of Surgery. I use a lot of their data, and that's a semi-annual, annual report. So if I'm only doing something once or twice a year for somebody, I really don't care about the time taken, because if it's only coming like once a year, like whatever, if I have to let the program run overnight on the computer, it's not the end of the day. It's okay. However, if you have something that, for example, like API calls, where you want that data to update as frequently as possible, in that case, you might want to give up a little bit of accuracy if you're going to save a lot on speed, if it's a very large data set. So that's something that's cool about this, is just kind of seeing all of these run at once. So if you look at some of these here, with this code, the ignore warnings equals true. So some different models are kind of finicky when it comes to like the way certain code is written or the way certain models exist. Some are more sensitive to missing values, for example. Same thing here with custom metric argument. That's something cool. You can actually add in custom metrics to this if you want. But again, we can set it to none and choose the defaults here. So if you look, all these different ones come out. So the issue, I'm trying to think, okay, so if you're having issues with this, I'm guessing it's because we have our bagging XGB classifier and AdaBoost classifier in here. So there's a couple of those that are reliant on those prerequisites being installed as well. But yeah, so a lot of different ones here. So if you've ever kind of seen any of these looked up, here's some other options too. So it runs through all of these for us. So that's the example with the classifier. Let's go ahead and do one as well. This one will be looking at that Boston housing data. So we can go ahead and say Boston. And say is equal to datasets dot load Boston. And then this one will look a little different how we split our data here. So I'm just kind of showing you a couple different ways. So this is shuffling, just getting it in different orders. So this data had some inherent order to it. So if you ever have data that kind of comes to you and it's already in order, I guess you could say, and you want to do a train test split, something to think about there is using shuffle like this, because it allows for you to, I guess you could say, I kind of mix things up. So if you have data that's ordered and you want to get a random training and testing thing. So here we have these imports here. So we have Boston.data and then Boston.target. So the data is what we're looking at to learn from. The target is what we're trying to reach. And again, our random state just keeps things consistent for us with our data. Here, we're going to do one other thing because of something, the way it's going to read it. And since this isn't the total focus, I'm kind of, I guess you could say, shortcutting this a bit for you all. So we're going to go ahead and take something that's going to be not initially read as a number, and I'm going to say it's a number here. So I'm recasting. So sometimes when you work with data sets, Python misinterprets what they are. So in this case here, we're just switching something to make sure it's all read as numbers. And then this is just looking at some flattening here to get things kind of in the order that we want. So I'm going to go ahead and run that. Oh, where is it? Not liking. Data set is not defined. Which one is it saying is not defined? I spelled Boston wrong. Let's see if I run this separately. Data sets. I need an S in there. There we go. So it should be data sets, not data set. So it's kind of reading in our data here, and then we'll do our splitting. So again, I'm gonna get typed real quick here, then I'll walk you through what it means. So what we're doing here is when I'm splitting this data up, I shuffled it, I recast it here to get a float, and then the offset is just pulling here. So you're looking at a certain chunk of that data. So we're just replicating here if we only had limited data instead of using the entire thing. And again, a great part about building up these repositories here is you just have a ton of example code. That way that you can look back at it and then kind of see, different ways that things might be done. So another thing here, again, whenever we've defined models, I've just always used the phrase model. Now that we're seeing a classifier, it can be abbreviated CLF. Typically, regression-based things are also kind of keyworded as reg. So here we want our lazy regressor. I'm again going to set that verbose equal to 0. We're going to ignore some warnings. We can kind of see if we get those warnings, what they're going to look like here. And then we'll yet again leave our custom metric equal to none. And then we have models dot prediction or slash predictions here. And then we're going to say regression. So our regression model dot fit x train, x test, y train, y test. So I'm going to go ahead and put that in the shared. And you could put all this in just one block of code. I just try to space it out a little bit so we could talk through it a little more. And if we want to go ahead and look at it, here is all of our regressors. So here we have adjusted R squared and R squared. The R squared measure of standard error, and then the time taken. So here's some new kind of cool ones here. Again, not always necessarily the typical ones that we see. You could also see there's a ton of regressors being executed here pretty quickly. So some cool ones in here that we didn't necessarily talk about that I want to. If we're looking down here, so if we go down to, for example, Poisson. So this is a specific regression technique used for a different type of distribution. Great question in the chat. I'll get to that in 1 second here. So with these different types of distributions, sometimes, like if I look at here, like if I just say Poisson distribution. So here's a cool visual. So looking at a Poisson distribution, you can kind of see the different heights of it here. Whereas this one here at lambda is equal to 10, it's pretty much a normal distribution. However, the default of a Poisson is up here is going to be at that being equal to 1. So we can kind of see the different outputs there. So here's another good picture of it, kind of seeing the differences here of how a Poisson distribution may differ. So as you get more advanced in your modeling, sometimes you find that data fits one distribution better than others. A good way of figuring that out is by looking at our regression techniques here. So I could see that Poisson did not perform as well as some others up here, so I may not say it's that. But however, if this had a really good accuracy here with this, with the adjusted R squared and R squared, then it might be an indicator that that's the type of distribution I'm dealing with. Okay, so essentially what it does is with this specific one, so typically in .fit, the main things we're looking for is the training data, and then so data comma target is a good way to look at it. That's kind of the XY, so like here would be like a general way of thinking about .fit. So here it'd be like X comma Y. So X is our features, Y is the target. However, with lazy regressor, since it outputs this all at once, so typically when we've looked at evaluating our models, we've done it kind of in pieces. However, the .fit command with lazy regressor specifically also intakes these two additional arguments here, just so you can see the whole table at once. So the reason why we go in that order is just specifying what it is. So you give your X data first, train test, and then the Y data of train test. So yeah, you do want to stick with the correct order for this one. So if you want to give yourself that note there. So when we run it, we can kind of see that thing again there. So each time it'll give us that same result because we set our random state the way we did. The only reason why you may get a different result than me is this bit here with the shuffling. So hopefully you feel a little more confident now in ways to implement pretty much every single regressor or classifier possible. And something cool about this, the reason why you want to look at this is because it helps you avoid having to, if you want to look at these though, it's kind of cool because, so something we deal with in modeling is a lot of hyper tuning. So if we look at these, again, we can kind of see here just how good a model can be without any extra work on it. So we're not doing any type of level 0, level 1, stack training or any of that. It's just a general like, hey, look at all these different models and see how they do. So if you want to look more into some of these models, that would be something you could definitely, if you just Google search this, it'll give you some cool resources and probably some examples with it as well. All right, so with that, I'm gonna go back to my slides here. All right, so we finished that up. Okay, so now let's talk about TensorFlow. So the whole idea of TensorFlow here is it's kind of one of those like very popular, trendy, like new ways we do things. So it's going to be a pre-built kind of machine learning library. It's got a lot of cool features in it, and it works with some really complex data as well. So it's an open source library developed by Google primarily for deep learning applications. It also supports traditional machine learning. So the idea of deep learning now is what we're going to kind of be really focused on here. Is it's like a, I guess you could say, an enhanced version of machine learning. It was just originally developed for large numerical computations without the idea of deep learning in mind. So the whole concept of deep learning, I seen a really funny post the other day. Anyone who tells you they're an expert in deep learning is a lot like saying you're an expert in medicine in like the 1800s. It's the concept that this is so kind of cutting edge right now that even someone who's like really, really good at it doesn't know everything about it. So if anyone's trying to tell you that they're the, you know, the definitive authority on this, you know, I really don't think we've discovered all the different things deep learning can do yet. So it's the idea of, you know, intaking data, performing a ton of different model fitting on it in what's called a hidden layer, and then outputting something we can use. So the idea of layered learning here. This is something definitely too, we don't have time necessarily in this class to go through all of the theory behind it. I want to get you guys that kind of hands-on application. I'll do my best to share some notes as well to give you the best understanding we can there. I know I didn't really do much note taking in the last thing with lazy predict just because we've done a ton of modeling already. So this will be a little more kind of hands-on, maybe less code, but more focused on the understanding. So for our input layer, just think about like the data coming in, right? So how's the data look? How does it come in? The hidden layer is really what kind of makes deep learning a bit different from our typical machine learning. So this layer processes data by performing computations and feature extraction. These layers have weights and biases that are continuously updated until the training process is complete. Each neuron, so each piece of that learning layer, has multiple weights and one bias. So this is the part where, again, we don't necessarily have a ton of time in class to go through all of the textbook style learning with this. So this is something, if you're looking during the week, you definitely want to try to do some research on your own on. And then lastly, we have our output layer, so where the data comes to. All right, I'm gonna go ahead and use that same Jupyter notebook I had. And I'm just gonna put some spacing in here just so I can get like a little bit of a gap there. All right, so let's go ahead and get started here. Now, the first thing we're gonna have to do is you're gonna have to install this. So that's this site here. So it's Visual Studio. I'm not positive on the differences on how this would work on a Mac. You may already have something similar installed. Same thing if you're running Linux. Let me see here. So we might need to do a little bit of troubleshooting here. Hopefully there's something similar on here. This is free though, you shouldn't need to log in or anything to download. So choose the appropriate one for your system. It's most likely this one here. ARM64 is if you're using like, I believe an older Surface, I think had ARM, potentially the new ones, if you don't have the pro level on that. But this would be the one that I had to use, and I think most people would as well. What I'm gonna do is kind of talk through some more stuff here is with TensorFlow. So let me go ahead here and, all right, a couple people caught up. So while we're getting everyone caught up on that, so here, let's talk a little more just about what TensorFlow is. And we'll spend a little bit of time kind of looking at this diagram as well. So this is through TensorFlow's site. So giving them credit for this nice diagram here. This is the latest version of TensorFlow that we're going to be installing today. So if we think about this idea, the idea of reading and processing data. So this is kind of the command we'll see, TensorFlow.data, and then the feature columns. We're also going to use Keras, which is part of TensorFlow. So kind of like a backend in there to actually process. We have some estimators. We're going to distribute, and then this is referring to how it's doing the learning. So this is that idea of the hidden layer. So our input layer, our hidden layer, which again, I want to talk more in depth about, comes out here to a saved model. So that's our output layer. So here are the three layers we're seeing: input, hidden, output. And then up here in our deployment, here's just some different options. Again, you can kind of see the different ways that it's used. If we're looking at this, just some other cool stuff about TensorFlow as well. So the key idea here is some cool companies that use it. So obviously Google uses it because they are the main developers. But you can kind of see here all kinds: Twitter, Airbnb, Coca-Cola, a lot of major companies around the world do use TensorFlow in some capacity. Keras, again, is giving us that ability to train within the TensorFlow framework here. So that we have deep networks. So here are hidden layer or layers, and then our outputs. So again, a lot of these diagrams are really complex, and for the sake of time, we can't necessarily get a ton of typed up kind of deep in-depth notes. I want you guys to have more of the hands-on approach today. But again, as we go forward, we will spend a little more time talking through what each piece is doing. All right, so to get this installed, I'm going to use that command prompt again. So if you're on Windows, you want the Anaconda command prompt. And if you're running anything else, you're just using the terminal there. So first thing I'm going to do is I'm going to go ahead and say pip install TensorFlow. Also, depending on your internet speeds, this one may take a minute or two, but positive side, once we have it installed, we won't need to again. That's an odd error. I think this is just coming up because I already have it installed on mine. Might have been because I had a VPN on. Let's see if that was the issue. So again, this one is a pretty big install here, so it may be taking a little longer. Once yours does successfully execute, what you're going to want to do is then go ahead and restart your kernel as well in that Jupyter notebook. All right. And that we can go ahead and get started here with using TensorFlow. So again, if you wanted to restart your kernel, I do already have it installed on mine, so I'm gonna go ahead and move forward. So what we're gonna do here is our typical import with TensorFlow is gonna look like import TensorFlow as TF. Let's see if now that error is gonna go away on mine. Fantastic. Okay. So I was getting that error because I already had it installed, so it was reading it twice. So that's going to be our first import there. And then what else we're going to want to do here is, again, that idea of TF is just a shorthand. So same thing with, pandas is PD, NumPy is NP. And then we'll kind of bring in a couple other ones here as well. So I'm going to go ahead and say TF. Actually, we put this all in one. TF.logging.set. So what this is doing is just kind of adjusting how it sets up the verbosity. So we're only going to log errors if we have them. We'll also be using NumPy. And matplotlib here. And I'm updating that shared file as well. What did I spell wrong? Why is it not liking that? Okay, let's strip that for now because I'm not sure why I'm getting that error. So we'll get rid of the logging thing, so it'll be a little more in depth in our logging there. All right. So moving on. So what we're gonna do here is we're gonna create some data here to work with. So we're gonna work with some predictive data here. So we're gonna be using an idea of budget and gaining data. So when we want to go ahead and set this up, we're going to go ahead and say our market budget, and we're just going to build an array here. So np.array. So this is a way to build an array from NumPy. So when we talked about a lot of different variable types now, this is just a different one. So I'm going to go ahead and build out some data here. So let's go 60. Actually, let's just make this kind of quicker. So let's go. And again, I'm just kind of choosing some random numbers here. So good. And then we'll get our gains. And then for these, let's see. How many I have in here? 1, 2, 3, 4, 5, 6, 7, 8. I'm also just trying to make these make sense right now. So give me a second while I type these in and we'll talk through. All right, so I'm gonna go ahead and put those over there in our shared code. So here we're just creating some data to work with. So 2 different arrays, both with 1, 2, 3, 4, 5, 6, 7, 8, 1, 2, 3, 4, 5, 6, 7, 8 different values. So we're gonna put those together. So what this is basically doing is it's gonna kind of give us a list out on data. So we're saying a market budget. So if we're budgeting 60, this is how many new subscribers we got. So our gains are the gains of subscribers. So if we want to go ahead and maybe annotate this a bit more. So if we're thinking about this in any type of marketing scenario, we're kind of looking at that general rule here of how we can predict if here's my marketing budget, here's how many subscribers I gained based on it. And then let's actually use one more thing up here just to specify this, just to make sure that our data type comes in correctly. We're gonna go ahead and just do a specifying the command that we're gonna make them floats. It should read it fine, but again, it's one of those things whenever you're creating data, if we use the idea of just specifying there that it's a float, it'll just make sure we don't have any odd errors later on. So let's go ahead and take a scatter plot look at this. So we brought in that plotting feature there. So we can go ahead and say PLT. So that's referencing our matplotlib.pyplot. Let's use a scatter plot here and we'll say our budgets are our x-axis. And then we'll use those subscriber gains as our y. So this is something we haven't talked through a ton of making these visuals. So if I just run this as it is, it pretty much gets the job done here. I don't like this output. Kind of always bugs me there. So the part that we want to get rid of that is you just say plt.show. By running that, it gets rid of that kind of annoying output at the top here. Our limits are fine as defaulted. They pull, you'll see some people like to specify their limits. Maybe if you want to get the 0 in here, that would be ideal. So if we want to kind of set those limits here, so you can say plt xlim and then plt.ylim. So kind of like in our general formatting, you typically want to have the same scaling here when you do a scatter plot. So when you scatter plot from 2 arrays here, it's not going to, I guess it looks at both of them independently. So on the scaling here, so this one just had the smallest value, and then the smallest value here was 20. So maybe we want to set those both starting at 0. And then here, if I look at my largest value in this one, let's see, we go up to like 110. So maybe I want to make it a little higher. Maybe I want to go like 120. And then here for my Y limit, I got 250 in there. So maybe let's go a little higher and make it like 275. So now you can kind of see that 0, 0 scaling there. So it makes it look a little nicer. Some other arguments here, you could use plt.x label and y label if you wanted to make this graph a little more informative. And then we can kind of label it here. So our y-axis is number of subscribers gained. And then this was our marketing budget. So again, just some ways to kind of customize a quick scatter plot there to look at it. So if I'm looking at this, like it looks like a pretty good, like, maybe I could use some linear regression here, kind of get a predictive model, but we're gonna kind of see how TensorFlow can be worked with data like this. Now we've already got that train test split brought in from above. What I'm gonna do is just kind of get it again, just in case you restart at your notebook. So I'm gonna go ahead and grab that from the top. So this is another way. A lot of times in sort of like tutorials, you'll see that like they bring it in as needed. So I always kind of try to do the data dump of like, here's all the imports you'll need. So if you ran it recently, you don't need to run this again. However, if you did restart your notebook, you might need it there. And then let's go do our split here. So actually, let me go ahead and update. My bad, I forgot to update the code shared file. Go ahead and put that scatter plot in there. All right. So we're gonna go ahead and split this. So we're gonna do X train, X test, Y train, Y test. So our marketing budget, and then our gains, right? So we named it, yep. And then we can go ahead and say, let's just specify our test size here. We'll just go 0.2. So just kind of giving that 80-20 split, and then we'll throw in a random state. And I'll share that over now. So by now you should feel pretty comfortable writing these out. You know, that's kind of the standard order we pull from there. X train, X test, Y train, Y test, and then our split. Again, we can play around with the test size. If you actually look up the documentation, you could specify either the test or the train size, but you could just pick one of them, and then, you know, by default, it calculates the other because they add up to 1. All right, so what we're looking to do next is we're gonna go ahead and create our model here. We're gonna start simple with what's called a dense network. So we're gonna kind of look at this, the idea of how many layers here and how many neurons. So this is kind of where that theory gets in a bit more. So for finishing up today, we just want to kind of get together our basic coding. And then tomorrow we'll kind of talk more about how to customize different layers and understand a little bit more of what it means. So to do this, we're gonna get our first layer. So I'm gonna go ahead and type this out, and then I will explain what it means. So if you want to go ahead and put that in. So a dense layer is just a singular layer with a single node. So the input shape of 1 here, this is going to kind of specify it's a single value. So we're going through there, and it's a one-dimensional shape because we look at that input here. So what we're putting in is our budget. It's just a single dimensional value. So this changes depending on how your input data looks. The number of units is figures out how many internal variables we need to figure out here. So since we just have the 1, it's just 1 there. So again, it's that idea of a single variable that we're learning from. So how many of those independent variables we're going to learn from there. So the idea of layering, it's kind of similar when we thought about the stacking, the level 0, level 1. It's in that same kind of mindset of ensemble learning, where you have different layers of learning occurring. So if you want to put together our model here, again, I'm just trying to think of all the different ways we can name things here. So mod is another typical one that people use. So here I can say tf.keras. We're going to use our sequential model. And then we're going to build it on that layer 0. So when we use a sequential model, which is one we'll see a lot of here, it's probably the most common, it's the idea of stacking our layers. So going layer 0, 1, 2, all the way through however many we may have. But again, we're building our first one here, so we're keeping it pretty basic, pretty straightforward. So again, the idea of starting with just layer 0. Another way you might see this, okay, perfect. Question about input shape and units again. So for input shape and units, if we're looking up, where are we? Right here. All right, so the input shape is going to be, I'm trying to think of another way to say this again. So it's the shape of your data that's coming in. Copy to collab, thank you. There we go. Thanks for the catch on that. Just put that one in there for the sequential. So with this, our input shape is describing our data that's coming in. So the input data I'm bringing in here is these one-dimensional arrays. So I am inputting, this is my array. This is kind of my target, or what I'm using to get to the target. So here's my features. It's just a one-dimensional array. And then my output here, my target is also one-dimensional. The number of units refers to how many of the independent variables there are. So sometimes the input shape of our array, we may have a rectangular kind of square, like a 5x5 matrix that all is just how the data is sorted. So typically when you want to use input data, if it's just one variable, it's easiest if you kind of make it that nice singular column. So let's say I have a spreadsheet of data that I'm reading in. The first thing I'm going to do is, if it's kind of ugly formatted, is just do a quick reshape of that just to make it all in one column. It just keeps the input shape a bit simpler. As we get more advanced with this, we might be learning from multiple variables instead of just one. So then that input shape would change. And then the units, again, is just referring to how many different variables we're learning from in there. So we'll kind of see some more customization with that later on. Other times you see Keras things built where the models are defined within. So I'm going to go ahead and just say another way we could do this. So another option here, is instead of predefining it, you can kind of do it all at once here. So I'm just going to call this one model. We could say tf.keras.sequential. And again, the idea of sequential just specifies the order that we're going in. So this is kind of another way of doing that. So for this whole thing here, it would just be inside. And then this would be read vertically. So maybe I have a bunch of these in here, but for what we're working on, we just have the one. This is just another option for defining it. So if you're looking up different tutorials and you notice like, well, wait a minute, why is he telling me to define it here? And then it's, looks like this. This is kind of the more like, I wouldn't say industry standard, I'd say shorthand way of doing it. So I prefer kind of defining my layer 0, layer 1, layer 2, whatever it may be. Whereas as you get more advanced, when you have a model, if you're looking to just have short kind of quick code, you can do it this way and it'll achieve the same result. So if we write it out this way, just the way Python runs, it runs top to bottom. So this would be our layer 0. If we had another one, it would be the next one for layer 1. All right, so the next thing we're gonna do here is when we build a model is we want to use compiling. So this is the idea of putting a model together. So it gives us what's called a loss function and an optimizer. So loss function is kind of saying like how much accuracy we're gaining or losing as it builds on, as well as how much of the data is kind of being diminished. And then the optimizer is saying kind of how we want to pick those out. So I'm going to type out an example here and then we'll look at some documentation. So I'm just going to use that mod I described earlier. So .compile. So we're going to use the mean squared error here for our loss function. And then down here, I'm going to pick out my optimizer. And then let's go ahead and look at some of those options. Let me go ahead and get that for you. So if you check out what I just shared over in the chat, and again, I definitely suggest saving some of these sites just because it's handy to have them where we need whenever you're looking at the documentation. So here it's our optimizer. So we have some different options here of the different optimizers we can use. So again, these aren't necessarily the greatest descriptors here, but if you click on them, so let's say I want to use like Atom, we'll use that one today. It shows you some more of the options within it here. And then here's kind of more of the, I guess you could say, dictionary or textbook definitions here we can see. And then some examples of it being implemented as well. So this is where kind of you learn the difference between like someone who can do machine learning or use TensorFlow and someone who really understands the differences. So like the parameter tuning within here. So for our, again, introduction point today, we're just going to keep it simple. We're just going to say dot atom. And then let's see a good value here. What do they say it's between? So if we're going to go ahead and specify our thing here, let's just use we'll use 0.1. Those are kind of the defaults there. So let's just go with 0.1. So again, with limited time, we will try to talk more about this each day in class, but I want to make sure that we can kind of get something we've worked through today, just so you can kind of see the idea of the workflow here. So I'm going to go ahead and let everyone get caught up for a second here. If you're looking through some of the documentation, I shared over the code in Collab as well. And then kind of thinking through what these things mean. So kind of getting that vocab in there as well. So what a loss function does is it picks how we're looking at error. So mean squared error is probably one of the most common loss functions we use. There is others, but that's kind of like our, I guess, our go-to. So what we want to do is try to minimize that. So if we think about it in this linear example that we're looking at here, if I go back up, our loss function, if we drew a regression line, it could be thought of as the residual. So the distance between the predicted and the actual value using a regression line. But again, when we get more advanced in TensorFlow, it's not always linear. Hence why we call it a loss function, just not the residual value there. And then the optimizers, so those different options we've seen, those are ways of, again, trying to adjust things while it's learning to reduce that loss function. So what's cool about this is these are kind of the idea of that self-learning model. So when we fit the model below, what's going to happen is it's going to look at each point and then figure out what the loss function is. So when it runs its first prediction, it's going to see what the loss function is and each time try to reduce it. So that's the idea of the optimizer taking its job in there. So we're going to see that it's going to start off and we'll see the verbose here of like kind of the output in the steps each time. To get the idea of Atom here for the optimizer, it's one of the optimizers. So it's just different kinds of algorithms that they use to optimize these functions. Let's see if we can find a better. I prefer sharing kind of their formal definitions here when we have these, just so I can kind of show you guys exactly what it means. Let's see if they have a nice definition somewhere in here. So what it does, it has these two other optimizers kind of embedded in it. So looking at the root of the mean square propagation, as well as adaptive gradient. So these are, again, this is kind of the part here where if I am suggesting reading outside of this course, it would be really looking back at, what definitions you're really going to need to do this. Again, the purpose of this is to get you more some hands-on code that you can see how it's executed. And then as far as like the extended learning, this is where that's going to come from. So Atom is just the optimizer we're choosing. And if you're looking for more on that, this would be a great read for you to do outside of class time. And if you checked out that other site I sent before, it gave you some other options there as well. Okay, awesome. All right, so let's go ahead now. We're going to go ahead and train this model and kind of see how it's going to work. So we're going to go ahead and fit it. We don't get to fit it at once. Sorry, my bad. So go ahead and say this is our trained version of the model. So I'm going to say mod.fit. And then I'm going to tell the order I'm putting in. So I'm going to put in my training data. And then here, we're going to go ahead and say epochs is equal to 1000. And we'll say verbose is equal to false. So in this case here, the things that we're putting in are going to be how we're fitting and training this model. So this is the argument I want you to use, and I'm going to kind of play with it a little bit on my end of what we can see. So for this side here, epochs is a specific argument of how many times to run this. So I'm going to go ahead and do it kind of shortly here first. I'm just going to say 10, and then I'm going to set verbose is equal to true. And I'm going to show you kind of how it looks on my side. So this is what it looks like when we're running this model here. So the things you're going to see here is an epoch refers to, again, how many times we're training it. So obviously more is better in this regard, but depending on complexity of data, that may be a longer amount of time. When I've trained on larger data sets, there's times that I've had to, kind of let a program execute overnight and then come back later on. So when you kind of look at that, it's one of those things where in a demo, we may or may not want something. Same here, if I set my verbose is equal to false, it doesn't show this. So this is just kind of showing you what it is doing. So it's running the model in the first one. Here's how long it took for each step. So again, seeing the execution time and the loss function here. So after this loss function occurs, so it's the sum for all those points together, it then tries something a little different. So it uses that atom optimizer, and then I can see each time this runs, the loss function gets smaller. So if I go ahead and run this now with 1,000, and I'm just going to go ahead and set this, I'm just going to leave it true. Please don't leave it true on yours. It'll look really ugly. I'll be fixing mine in a second. We can see it's going through it now, and you see mine is still executing, and it's finished. So if I go through here, here's my loss function up here. I can see it's getting smaller and smaller and smaller. So as I continue to go, and notice there's some increases, right? So like right here, I was at 595 and then it went up. And then it kind of fluctuated, it's hovering. Okay, then it found something again. So this is that optimizer working. You'll see a couple of fluctuations throughout where it gets higher. So like going from 429 to 430. So it's trying something different there. And you'll kind of see that all the way on down. But again, the more epochs you're running, the more time it has to learn. So if I get all the way to my bottom here, I'm at 118 is my loss, as opposed to way up here, we're at over 14,000. So the way you should run it would be like this, where it's just false. And then it kind of looks clean. All right, so let's go ahead and we're gonna look at our training statistics here. So we're gonna kind of see what this model looks like visually. So we can go ahead and say plt.plot trained. I'm going to say dot history, and then we're going to look at the loss here. So this is the way when I executed that my loss function was working. So I kind of notice here that it continued to go down and down and down at a pretty predictable pace, almost, like exponential here. So exponential decay. So this is my number of epochs, and then here was that loss. And then I'm gonna go ahead and update my, and then if we want to get rid of that annoying output thing on the top, again, that plt.show. So something we could think of here is doing some predictions with this. So now that we have a nice model we've put together here, we've lowered that loss function, let's go ahead and check out back up here. So if I want to do some predictions, so the key idea here is the goal of building a model is to predict with it. So if I used my budget here, that's what I'm trying to use to predict those number of subscribers I'm gaining. So let's look at maybe like 75. So that's kind of in the middle of our data. Let's see how that looks. So to do that, I'm going to say model or just mod.predict. I'm going to try to call it mod up here. So mod.predict, and then I'm going to go ahead and just put an input value of 75. So it's giving me the predicted output there. So if we look at 75, just from the regression, somewhere in here, we're looking at around that idea of 180, looking pretty good, right? If I use something that's in my data, so if I look at the actual values up here, Well, for 80, I was going to get 200. So let's see if I go ahead and do that prediction with just 80. Pretty darn close, right? That's getting really close to that 190, so pretty close to our idea there. So overall, pretty cool stuff here. What we could also look at here is the idea of using our test values and then comparing it with the predicted values. So we can go ahead and use our test values. So I'm gonna go ahead and just name some y predicted. I'm gonna say mod.predict, and then I'm gonna input that testing data. And then here we can kind of use a nice little print statement. So the real values, and then I'm just going to use a little bit of print forming here to get a tab. So that's /t. And then I'm going to go ahead and say y test. And I'm just putting a couple of spaces in between here. And I'll share this over in a second. Oh, what did it now? Oh, forgot a comma. There we go. And I spelled wrong. All right, reshape. There we go. There. So this is kind of giving us a way to, or not the chat, the shared file. Look at our output here. So kind of saying with the prediction, here was our real values, and here's what our predictions are. So not terrible. It seems like we're doing a little better on the high end. It seemed like that value here for that test was a little off. It gave me 80 to 116. So if we're looking at that value of 80 up here, so it looks like it pulled our 40 in there. So if I'm looking, 40 is probably going to be the thing with the biggest residual error too. So it's like, okay, that one didn't predict too well, but it seemed to do better on those kind of, you know, higher values. So maybe 40 was just a rough estimate. So maybe if I went back and retrained my model, I'd say, hey, I want to actually get rid of that because I'm finding out that that's not the best. The idea of exploratory data analysis, so EDA, where does this kind of come in with TensorFlow and our classic machine learning algorithms? So in general, these are kind of like hand-in-hand type things here. So TensorFlow is like a pre-built, it's like kind of its own thing. So machine learning, the way we've done it thus far is the idea of kind of doing it piece by piece. So evaluating different models, seeing which one works best or preferable over others, and then optimizing those. TensorFlow kind of has its own, like that epochs feature is kind of like the cool thing where it just kind of trains the model with layers. So if I'm doing a project kind of from scratch here, it's about ease of usage for me. So, you know, sometimes you might be able to kind of get, it might just be a project on like, hey, you know, let's look at the data and let's see what kind of trends we can get from there. So maybe you're developing dashboards. Then those dashboards may evolve into something that's a little more kind of, you know, the predictive piece to it. So can I build a simple model just within a basic, you know, machine learning kind of algorithm like we've seen so far to get to the prediction I want? If you're not having the success that you'd like with that, that's typically when we then kind of take it a step further into things like ensemble learning as well as TensorFlow to kind of amp ourselves up a bit. So TensorFlow is really popular with like big data, just because again, it's kind of got a lot of prepackaged built-in ways of dealing with that. So think of it as kind of like a hierarchy. And the more complex you get, the more potential challenge there is. But that's kind of where I look at when I get into this point of TensorFlow. This is more of the, you know, think big data. So yeah, the exploratory part, when we think about exploratory, we're more so thinking of, I guess you could say, you know, when we say exploratory, it's mostly the data visualization piece to it. So a lot of those visuals we've done, that's kind of where the exploratory stuff comes in, looking at different types of distributions. So if a client sends me a bunch of data, that's kind of the first thing I'm going to do with a new client is I'm like, hey, it's going to take me, you know, X amount of hours to kind of get a handle on your data, explore through it, learn the different parts of the variables. And then this is kind of more on the back end, like the advanced modeling piece. Another thing we can do here, just while we're doing this, is going to be looking at that R squared. So we can go ahead and pull in this, and I can go ahead and get my R2 score or my R squared score. So this kind of gives us that idea of our R squared. So again, how much of the variance can be explained. So higher R squared is better. The idea of how accurate it is. So we're at 0.87, which means that this, I mean, it's not a bad R squared, but it's also not great. You want to be kind of, again, closer to 1 is better. So if I got to this, something I might do is go back and look at where I'm pulling my data from. I might want to do some outlier analysis on this. So how we've seen in the past, we worked through outlier analysis. And the way we did that was we went back up here and we looked at our model, and maybe we took it, maybe we did some box plots to look at different potential outliers within our data. So something that might be an outlier here, this one is kind of our issue one, right? This 40 going to 80, whereas everything else kind of had a more discernible pattern to it. So we kind of, that was our one. If we looked at our output here, that was the one here that we had 80 go in and we got 116 out. So if we look at that, when we put in 80, it was saying 116 instead of 200. So that could be something maybe we look at as like, okay, this is giving me an error. I don't like how large that error is. So let's maybe look if any of these points could be deemed as outliers. So when you see R squared lower than you'd like it, kind of a rule of thumb is you want to keep R squared at least at like 0.9. And again, higher is better. But anytime I get an R squared below 9, that's when I'm like, okay, like I should probably go back and look at this data. Let's do a little more data analysis exploration here. Like, is something causing it an issue? So kind of summarizing what we've done so far, we went ahead here and we created a model with our dense layer, and then we put together a predictive algorithm here to see like, okay, so what can I predict based on the number of, or the amount of money in my budget, and then how much I'm going to look at in subscribers. So that was our big introduction there into TensorFlow. So you've used it to build a model. Also, if we kind of review back up at the top, we also learned about lazy predict here to kind of see how different models without any tuning or any adjustments were able to perform. So this kind of gave us that intro level into TensorFlow. Some things that we'll see as we continue on, we'll be doing work with what's called the MNIST data set. So I'm going to go ahead and just share a link over of that. I want to talk about that today just so we can kind of see what it's going to look like as we move on. Let me see. I'm just see if I could find just the general data set here. There we go. That's what I was looking for. So this is going to kind of be previewing tomorrow what we're looking at. So this is going to be one of your kind of like more famous tutorial-based data sets, I guess you could say. And what you use it for is essentially going to be a good example of how we train things here. So this is one of the cool parts of when it comes to using TensorFlow and Keras is that you can do some really cool stuff that's kind of uncommon, I guess you could say. So when we've typically looked at like numerical data, what's nice about this is because it's built so largely, it's got some cool stuff in here with looking at images. So it's handwritten digits. It's got 60,000 examples and a test set of 10,000. So we can train on 60,000 and test on 10,000. So this is going to be one of those where it's like some very specific code we use to pull this in. This is going to be the main data set we're going to focus on in the next couple of lessons here in terms of figuring out how to build TensorFlow into doing something a little cooler than linear regression. Because truthfully, you know, that idea of what we did there, that was kind of it's essentially just the same machine learning stuff we'd see if we did just basic linear regression on it. I just wanted you guys to get that intro level where you could see how to do it in TensorFlow. So if we look at this, here's some downloads. You won't need to do that. If you want to, you can. However, you don't need to. We'll be pulling this directly. So if you kind of read here, this will show you a little more of what it looks like, as well as some of the things we can do with it. So the error rates we should be getting. So kind of the standards of what we could see on here. So it's got a ton of documentation. Again, this is one of those when it's a big file set, it's just gonna be kind of how we see it. I'm just gonna put a quick visual. This is the more formal documentation of it. So kind of explaining where it came from, what it's used for, and a little bit of background on it. Let me see if I can get some images. So these are kind of some of the images here we're seeing. So what this is cool for is like, this is a good training example of working with the idea of handwritten stuff. So here, these are just like the first couple on Wikipedia. So the regular version, kind of just black ink on paper, and then the inverted version here. And then the idea of scaling it. So kind of here pixelating how it's going to look. So this is going to be the data set that we're working with and that we're predicting based on. So we're going to be looking at how well we can classify these. So if I look here, for example, at this row of 2s, let's see if I can get this image bigger. There we go. So one of the bigger goals, if we think of things kind of more like this idea of advanced learning or the more advanced idea of layered learning, is getting good at teaching a program to classify things here. So think of if your phone unlocks with your thumbprint or your face, whatever it may be, how it's learning that concept. And TensorFlow and this idea of deep learning really kind of builds into that. So for example here, teaching a program to recognize all these different variations of 0 as the exact same thing. So as someone who's taught in a math classroom for many years, I have a lot of this built into my head of different ways kids writing numbers. The one that comes out the most common here would be the 7 and the 2. So the idea of this 2 being kind of what textbooks use for some reason, but yet when we write 2s by hand, they kind of look more like this with a little loop. 7s too, if you've ever had a good math teacher, for some reason we all write 7 with this little line in the middle here. I don't know why, other than I guess there's the Greek letter gamma that kind of looks like a 7, like if you don't put this line here. So for some reason you'll see a lot of math teachers, myself admit it, we use that line in the middle. But teaching a program to recognize that this and this are acceptable variations, and the idea of human error in handwriting, it's not like when we type something. So this will be the kind of data set we're looking at here to make predictions on. And the idea of classification, so saying all of these things go in the same direction, in the same bin, and how accurately we can do that. One of the most common ways where we've kind of seen this increase in notability is Apple's latest thing that they're working on. So utilizing their Apple Watch is a kind of extension of the phone, mainly because people were complaining that when wearing a mask due to COVID restrictions, their iPhones wouldn't unlock with their face, which I don't know why people were really complaining about that, because like if I'm wearing a mask, I look distinctively different than I look now. So that would kind of defeat the purpose of a face unlock if like it worked for anything that sort of resembled my face. So again, that was kind of an issue they were having there, where they trained this algorithm on facial recognition. Where that kind of comes from is all the different Google Photos and stuff. That's how they were able to build that algorithm up so well, where it can kind of unlock just with your face at a couple different angles there. However, due to the mask restrictions, if you're going like this, it was harder to see. So again, they kind of tried to do a workaround temporarily with the Apple Watch for that. So that's kind of where this type of learning comes into play. The idea of having a bunch of different examples of something that could be there. So when you're doing this type of stuff, you are typically going to be working with demo data. As we get into these more advanced topics here, it's really not something we can create a huge sample set of data for that's actually going to be meaningful, unless I was going to do handwriting digits for a couple hours in between lessons here. So we will be using a lot of kind of pre-existing data there as well. As far as an assignment of something you could do before we meet tomorrow, I would suggest doing a little bit of reading up on this data set so we can kind of understanding a little more of where it comes from, what we're going to do with it, as well as if you want to look at any of these. So these different optimizers here, if you want to do a little more reading on what those optimizers are, that would be the most ideal thing there.